Let's move to the shortest path problem. So this problem could be considered a transshipment problem, but a special case of that kind of problem. We can start by looking at, or just to simplify it, we're trying to find the shortest path in terms of, let's say, duration. We can have that in terms of distance, and we can even focus on other values that you can assign, for instance, leaving from a place to the other, finding the route that gives you the, for instance, the most services on the route, or anything related to that, or the most scenic quality of what you see and what you get to experience. So in this kind of problem, we have one origin, which is the start point of the trip, and the destination. As I told you earlier, this is a special case of a transshipment problem where you have where you assign. So if you remember the previous problem, we assigned the number of cars to each of these nodes. But here, if we have a shortest path problem, automatically you always assign -1 from where you depart, and then +1 to the destination that you want to reach. And all the nodes in between are going to get zeros. Let's look at this example. So you and your friend are planning to travel from Birmingham to Virginia Beach, right? And there are several ways of doing that. For each one of these arcs leading to the nodes in between, we have the duration. So it's going to take us 2.5 hours to drive from Birmingham to Atlanta, for instance. And there are also points concerning the quality of that route. It could be based on the scenery that you see. It could be also based on, for instance, the quality of the road itself. So driving there is easier, or it could be like better roads, for instance, better road conditions, and so on. All right. But in this case, we have these 3 points that represent the quality of the scenery that you get to experience from, well, across all these roads. All right. So on the map, actually, it looks like this. You have Birmingham here and Virginia Beach right there. And this is in the US. So you're driving across Atlanta and North Carolina, Virginia. There are different ways of doing that. These places are quite foresty, and there are many ways that can lead to Virginia Beach from Birmingham. Now, if we want to go back and start working with our Excel sheet, so differently from what we had in the previous example where we said the number of products shipped, we are going to assign this a route, let's say route. So any route that gets 1, that is going to be decided as our selected destination, all right? Then we have from, and again, city, from city to city. And then here we have 2 values. We have the duration, time, for that route, and then we have route quality score. All right, and then similar to the transshipment problem, we have also nodes. Okay, 1, 2, 3, 4, etc. That could be a city, and we have the net flow, which is the left hand side that we calculate, and the right hand side is the one that we want. It's going to be right hand side, supply or demand, right? Supply and demand, or demand. Now we know from this that our first node 1 get 1 starting here, 2, 3, 4, 5, 6, etc. So we're going to start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we got 11. So just not to make this video quite long, I'm going to ignore the city names, and I'm going to stick to the nodes themselves. I'm going to hide this, and then I'm going to start with the right hand side. So here I'm going to say that I have -1, so this has to equal -1. This node, the net flow here, has to equal -1. Everything else is 0 except for the destination, which is Virginia Beach. So that's going to be, this is going to equal 1, and everything else in between should be 0. All right. Now the route itself, if our model decides this is part of our route, it's going to be given a value of 1. So we have only 2 values that can be selected. It's either 0 or 1. All right. How many routes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So we got about 18 routes or 18 arcs. So this entire range here is going to be our decision variables. All right. So and then we start from the nodes, and as I said earlier, I'm going to ignore the cities for now just to make this reasonably long video. So we've got from 1 to 2, and then 1 to 3, and then we've got from 2 to 3, and 2 to 4, 2 to 4, and then we've got from 3 to 5 and 3 to 6, 3, 3, and then 5 and 6. And then 4 we've got from 4 to 6 and 4 to 7, 4, 4, 6 and 7. And then from 5 we've got another 2 going outside. So from 5 to 9 and from 5 to 6, 5 to 6, 5 to 9. And then 6 we've got 2 departing arcs. We've got from 6 to Luxembourg and Greensboro. So we get 8, 6 to 9, and then from 7 got going to 8 and 10, 8 and 10, talking about these 2 arcs, and then from 8 we have 8 to 9, 8 to 10, so 8, 9 and 10. Then 9 we've got 1, just going from 9 to 11, and then finally 10 to 11. All right, for each one of these we have the times. So basically 2.5 for the first, 3 for the second, and then from 2 to 3, 1.7 hours, and then from 2 to 4, that is 2.5 hours. Then from 3 to 5, 1.7 hours, 2.8 hours, 1.7, 2.8. And then I'm gonna actually copy and paste the rest just for the sake of this video. All right, so this should be the complete numbers associated with each arc, where we have the route from 1 to 2 has about, or it takes 2.5 hours. So if we want to minimize this, it's going to be the total time minimized. It's going to be the total time. So this is going to be sum product again. Solver is going to decide whether each one of these is included or not. If it's included, it's going to be 1. And 1 times the corresponding time gives us or includes that corresponding time in the route. So it's going to be this times that. And if we want to maximize the scenery or the scenic quality, so that like we see more of the nature from Birmingham to Virginia Beach, then that's going to be a maximization of, again, whatever that is being included from the route column against the route quality score. All right, sum product. So these two, we are not going to consider both. We're going to consider one at a time. And this one is this column here is our constraint column, as we did in the transshipment problem. Now, let me come to the net flow calculation. And this is where I introduce a new command that you've probably not used before. You're going to use this for the first time. It might look quite, let's say, complicated, but we're going to break it down so that you understand what's going on. Now, just to remind you that any arc starting from this number to that number is going to be minus for that node, because it leaves 1. So anything that leaves 1 from here is going to be minus. So in that case, it's going to be minus this number, right? Now, instead of just trying to find all the ones that have 1 here, let's just for the sake of explanation, let's assign these two numbers, 2, 2, and 3. So you see here, it captured minus these 2 because I just wanted everything that leaves node 1 to any of the other nodes. We have 2, which is from 1 to 3 and from 1 to 2. All right. Now, instead of doing it this way, I can use what we called SUMIF. SUMIF. Now, I want that summation to be in minus because these are leaving, right? So SUMIF. I want Excel to search through this point of origin nodes and look for 1. If they will find 1, they will sum what? What is that? What is it that I want to be summed? I want that the values in the decision variables to be summed. All right. So what would that return then? Again, it will return minus 4. If I change that to 3, it will consider that as well. If I change that to 3, it won't do anything because that is not 1. So the criterion here is 1. All right. So that way I don't need to do the calculation manually. All I need to consider here is whatever that is leaving is minus whatever that is going towards this. So if we find any 1 here, that is 1. That's going to be considered, instead of adding minus, it's going to be just sum f. Again, look through the 2 range, looking for 1. If you find 1, then sum that range, the corresponding range. So sum the values corresponding to that 1. We don't have any 1 here, so this is going to return 0. Because we don't have any 1. We have only a node that sends or that gives you the option of moving from 1 to 2. These are the arcs that are available. But if we change that, for instance, to 2, let's say 2, want to modify the ranges again. Now, I want to find where 2 is received, and if 2 is the destination, this is going to be counted in plus, because I didn't add the minus in before this. So that way, I'm counting all the routes automatically without doing that like one by one. So I can do this for the entire ranges and have a generic function. So I'm going to consider any outflow arcs in minus. Please sum them, sum f, this range, which is the point of departure. This is going to be minus, sum these if they are 1. Now this range is going to be fixed, so I'm going to make that fixed with a $sign. And then what is it that I want to be summed? Basically the corresponding decision variable value. All right. These are all going to be considered. That way we are including all the outflows. How about the inflows? That would be plus sum f. Now this is the that was the outflow. The inflow, so the flows that are going into the nodes, this is that range, right? And by the way, this has to be also fixed. The $sign, again, this range is also fixed. What is the criteria? The criteria is 1. So if this has 1, consider that and add a plus sign to it. What is it that should be summed? That's the corresponding range, basically. Again. So what this function does, in short, is that it actually considers if this route has as a departure point of departure has that number, it's going to consider the corresponding value in minus or plus depending on what you're trying to capture. If it's a point of departure, it's going to be minus. If it's a point of destination, then it's going to be plus. So that way you can basically just do that once and scroll this entirely downward, right? We're going to remove these numbers from here. If we check every time we are trying to find if 3 is found here, if 3 is found here, we're going to take the corresponding plus number. If 3 is found here, that's going to be, the numbers here are going to be included, but in minus, because we have the minus right there. All right. And that's the most difficult part of this. Now, do we have a situation where we have demand equals supply? Very obvious that we see that it's minus 1 here and it's plus 1 there. So in this example, if we go to solver again, if we want to say, like, if we want to find the route that would lead to the shortest distance, okay, we're going to do this. We're going to select the total time being 0, all right? And we want to minimize that. We want to have that minimization, and we want these numbers to be, like these routes, to be our decision variables. And then finally, our right-hand side and left-hand side. Our right-hand side is here. Left-hand side, our net flow, that should be now, because demand equals supply, this is going to be made equal. So this has to equal the corresponding right-hand side. Okay. Now, there's one more thing that we should be mindful of, which is the fact that this should be the values here should be between 1 and 0, but it's not actually between 1 and 0. They have to be integers. So what you can do here, you can add another constraint assigning these decision variables, and you can use integer. Okay, you can make that integer. So that's going to make these values as integers. They cannot be 0 point something. It's going to be always 1, 2, 3, or 4. Not only that, we want these values to be less than or equal to 1, right? Because they can always be 0 or 1, and they cannot be negative at the same time. With that, we are ready to solve our. And what you see here is this route. We are starting from. So this is the route that's going to minimize the total travel time to 11 hours, 0.5 in total. What would be that route? It's from 1 to 2, so we're going to take this one, and then from 2 to 4, 2 to 4, and then from 4 to 7, and then from 7 to 10, and then from 10 to 11. So this right here is the shortest route. But what if I want to maximize the scenic quality instead of following the shortest path in distance or in durations? I can basically just change the objective function cell and maximize this instead. I just want to follow the route that has the highest quality of scenery that I get to experience, and then I click solve. Here you see that this is going to take us a little bit longer. Maybe if we consider what we had 11.5 hours. Now this is going to take us almost 5 more hours roughly, but that's the best route when it comes to observing and experiencing nature, starting from the 1 to 2, 2 to 3. So instead of going 2 to 4, now I'm going from Atlanta to Chattanooga, and then from there to from 3 to 5 to Knoxville, and then from Knoxville to 6, okay, from Knoxville to Asheville, and it's going to continue that route that maximizes these points. All right, so this is supposed to be the how to solve and go about this type of problems. That's the origin, this is the destination. The duration is one factor, the scenic quality is another. You have to choose one at a time. Well, there is a multi-objective optimization, but we're not considering this in this course. So finding the quickest route through minimizing travel time is one problem. A separate one is finding the most scenic route, which is the one that we calculated. All right, so this was the shortest path problem. This is another way of modeling other kinds of problems using the shortest path, but we're not going to consider it in our course this year.